The battery has been competing with the internal combustion engine since the dawn of the automobile industry. Initially, electric cars held their own, as gas-driven cars were hampered by a scarcity of gas stations and by hand-crank starters that most consumers hated. A decade into the 20th century, gas stations began to proliferate, and electric starters replaced the cranks. Electric vehicles were left in the smog. But even gasoline-powered cars now needed a reliable battery to deliver enough power to get them started. Lead-acid batteries have been standard automotive equipment ever since. Originally developed in 1859 by French scientist Gaston Planté, lead-acid batteries later became the technology of choice for automotive applications. They're not only a rechargeable battery technology, but they're also robust enough to withstand the heat and vibrations under the hood, and relatively inexpensive to make. The East Penn Manufacturing Company in Lyon Station, Pennsylvania, has been cranking them out since the 1940s.
We have about 2.5 million square feet of building on about 520 acres of land. We make a wide variety of products. We have several plants on this site, producing everything from motor power batteries to stationary batteries to our largest segment of our business is the automotive battery industry.
First step in making an automotive battery is to make a grid, the framework for the plates. So what we're doing is we're taking hard lead, putting it into a 16,000-pound pot. We're melting that lead, wearing it into a book mold, and we're casting the grid work for the battery.
The grids then undergo a process that coats them with a lead oxide paste, aptly nicknamed mud. These are now the positive plates that will make up the cathode. On another assembly line, grids spool off a reel and are coated with a different mud concoction that creates the negative plates for the anode.
After making our positive and negative plates, we need to put a separator material between the positive and negative electrode. So what we're doing is we're actually making an envelope. This separates the positive and negative electrodes so they don't short out. The machinery behind me will take the polyethylene material across the top. That positive plate feeds in between the material. We seal it. Then it gets a negative plate on top of it. It counts how many plates we need. It's a 15-plate battery that we're making here.
The reason why several plates are used in each cell is to increase the surface area of the anode and cathode, maximizing the chemical reaction that produces the electricity.
The plate really designates how much ampere-hour capacity or reserve capacity, and the amount of surface area on the plates will tell you how much high-rate discharge capability or cold starting capacity you'll have.
A stack of plates comprises each 2-volt cell. 6 cells are inserted into each polypropylene case to make your standard 12-volt car battery.
The next step in the process is our assembly department, where we're going to connect those 6 cells to get a 12-volt battery. We're going to short check each cell. It will move down the line. We will spot weld each group together. From that point, we put a cover on the battery. We heat seal the cover to the case. Then we have to connect the internal post to the external post. Then it moves down to a leak tester. We don't want the battery to leak. And then we unload it to a pallet.
The nearly completed batteries remain in storage until it's time for the company to fulfill its orders. Only then are the batteries filled with the electrolyte solution that is 2/3 water and 1/3 sulfuric acid.
After the batteries are filled with electrolyte, there is no voltage there until we bring them into this forming room where they are hooked up and electrically charged to form the batteries. Once they are formed, they are a 12-volt battery, which then will be taken to our finishing department where we top the batteries off. We plug the batteries, we wash them, we brush the terminals, we put a high voltage rate test on them, and then they are labeled for our customers.
As lead-acid battery manufacturers keep cranking out big boxes for our cars, researchers in other fields are creating batteries so small they're invisible to the naked eye. The incredible shrinking battery could one day power a submarine through your bloodstream. In 2006, 160 AA-sized oxynickel hydroxide cells provided the energy for the world's first manned flight powered by dry cell batteries. The one-man aircraft flew for less than a minute and traveled about 428 yards. Batteries will return on Modern Marvels. We now return to batteries on Modern Marvels. Long gone are the days when our technology only stretched as far as the longest extension cord. We're hooked up to an arsenal of portable electronics that help us gab, compute, and rock on to our favorite tunes. Batteries have enabled us to power up while we're on the go, mainly by cramming more and more energy into a smaller and smaller package. Since the 1990s, the mighty little wonders powering much of our tech, including the Tesla and our laptops, are lithium-ion batteries.
The use of lithium in batteries has enabled a lot of technologies to come forth and become very, very small. For example, when cell phones first came out, they used nickel metal hydride technology. People refer to them as bricks, because that's exactly what they were. They were the size of a brick. Now, with a higher energy density material, cell phones have become smaller and enable a lot of other devices to be made. For example, an iPod could not exist in its current form without lithium technology.
Batteries have been shrinking quickly over the last few years, but only recently became microscopic. In 2003, University of Tulsa chemistry professor Dale Teeters and 2 graduate students earned a U.S. patent for their innovative method for making nanobatteries for the nanomachines of the future.
There was a movie in the 60s, Fantastic Voyage, about a submarine that could be injected into the human body to take care of problems that existed. Now, we thought that was science fiction, but today in Germany there's a company that's developing a nano submarine small enough to inject into the human body and go through the veins and arteries and eject chemicals or drugs where a problem may be.
Such intriguing technology can only be contemplated because of recent advancements pioneered by researchers like Dr. Teeters. He discovered that small porous aluminum discs, originally developed as a filtering medium, provided a superstructure to make more than 1 billion nanobatteries at a time.
One of the first steps in the manufacture of these nanobatteries is to check the integrity of the alumina films that have the 200 nanometer diameter pores. And so what Mira is doing here is taking one of our aluminum membranes and she's going to put it into a scanning electron microscope. We have to use a scanning electron microscope to see the pores because, once again, at 200 nanometers, this is one of the few devices that we can use to see it. And what we have up here is an image then of the pores that you can see. From that, we can see that we have a good membrane.
To manufacture these microscopic batteries, step 1 is to coat one side of the membrane with a tin oxide anode material. This also seals one end of the pores. Now the membrane can be turned over and the pores filled with a liquid polymer electrolyte. Then it's time to coat the top with the cathode material.
We place it into the sputter coater and we pull up the argon gas on the inside and we start by giving it an electric current. This electric current is going to create a plasma that you see here. What the plasma is doing is knocking off microscopic particles of our metal, and it's essentially dusting our substrate that's in the bottom of the sputter coater with these particles, which is giving us a continuous layer of lithium cobalt oxide, or our cathode.
Once we've manufactured the nanobatteries, we have to test them to see how they're going to function and also to test them to see how we can improve their performance. We do this with an atomic force microscope, which you see here. We put the array of batteries in the microscope here. The microscope has a tiny tip that actually can touch the surface, and we use that tip to make contact with the batteries. The tip, which we can see up here on the screen, touches the top of the nano battery, the anode, and then it completes the circuit just as you would touch a battery in any other device. And once we've completed the circuit, then we can do charge and discharge studies by using this sub-femtoamp source meter, which is a very sensitive instrument, but we need that in order to work with these very tiny batteries.
Each pore in the membrane is a battery. And like all lithium-ion batteries, each one outputs about 3.5 volts.
But because you're dealing with tiny, tiny batteries, the actual amperage that you can put out is quite small, picoamps compared to milliamps in a real-world size battery. But one must remember, if you're dealing with the nano devices of the future, picoamps will be sufficient to drive those devices.